In this lesson, we'll explore several ways to describe how much solute is dissolved in a solution. The type of concentration used depends on the state of matter of the solute and the intended use of the solution. The first way to express concentration is by a series of percentages. If you have two solids that you wish to mix together, it might make the most sense to determine the concentration by mass percent. Anytime you talk about percent, it means it's going to be the part that you're interested in divided by the total times 100. So in the case of mass percent, it would be mass of the solute divided by the total mass present. So mass of the solute plus the mass of the solvent times 100. So for example, what is the mass percent of sodium chloride if you have 5 grams dissolved in 95 grams of water? So I tried to set up the numbers so that it would be easy to work with. So we have 5 grams up top, a total of 100 grams in the denominator times 100 gives you 5% by mass. Volume percent, same idea, but this time if your solute and your solvent are both liquids, like say for example you wanted to dilute some sulfuric acid, for example. If volume, you might want to keep it as the volume of the solute. You don't want to be weighing them out. So volume percent is going to be volume of the solute divided by the total volume of the solvent of the solution times 100. So if we have 20 milliliters of ethanol and we have 80 milliliters of water, the total volume is going to be 100 milliliters. It actually isn't, but we're going to assume it for this particular problem. And then times 100, and we would get a 20% by volume. Mass volume is probably the one that you are already familiar with, in that we tend to want to weigh out our solute and then we're going to dissolve it to make a certain volume of solution. So mass volume percent is going to be mass of the solute divided by volume of the solution times 100. So for example, if we had 15 grams of sodium chloride dissolved in 100 milliliters of water, we would end up with a 15% mass volume per solution. Now for the most important concentration unit in chemistry, which is molarity. Molarity measures how many moles of solute are present in 1 liter of solution. It's defined as being moles of solute divided by liters of solution. And the unit for it is a capital M. Do not use lowercase m. That means something else when you're talking about solutions. So for example, what is the molarity of a solution prepared by dissolving 1.5 moles of sodium hydroxide in 500 milliliters of water? Well, we put our moles up in the numerator and divide by our solution in liters, our volume in liters, which is you just take your milliliters, convert it into liters, works out to be 0.5 liters, and you get a solution that would be have a concentration of 3 molar. More typically, you might be faced with problems where it wants you to prepare a particular solution. I mean, that's how you would that's what you'd be doing in the lab. So for example, how could 1.5 liters of a 2 molar solution of sodium chloride be prepared? So we need to have something we can weigh out. So we're going to find how many moles of sodium chloride are needed. So molarity is equal to number of moles divided by volume. So you rearrange it, you get number of moles is equal to molarity times volume. So we would have to measure out 3.75 moles of sodium chloride. However, you can't weigh out moles. You have to convert that into grams. So we're going to take the moles of sodium chloride and multiply by its GFM, or its molar mass, and we would get that we would have to weigh out 219.16 grams of sodium chloride and then dissolve it to a total volume of 1.5 liters of water. So this is an example from the worksheet that goes with this lesson. We want to find both the molarity and the mass percent of the solution when you dissolve 2 grams of solid sodium phosphate in 100 milliliters of water. So let's start with the mass volume calculation. So remember, mass volume is going to be grams of solution divided by grams of solute divided by milliliters of solution times 100. So switching to my pen, so we have 2 grams of solute, make my decimal point a little bit clearer, divided by 100 milliliters of solution. And we're going to assume that adding the solid solute to that much water does not change the volume of the water significantly, which is a pretty safe assumption, times 100. And we get that this is a 2% solution mass volume. All right, so the next one we're going to do is we are going to determine the molarity. So remember, molarity is moles over liters, and we have, which means we have to convert our grams of sodium phosphate to moles, and we're also going to have to convert our 100 milliliters of water into liters. That's easy, just divided by 1,000. So now let's do our grams to moles conversion. So number of moles is equal to our 2 grams of sodium phosphate divided by the molar mass, the GFM, so 163.954 grams per mole. And we get that our number of moles, and I'm going to put it up here just to make sure I leave myself enough space, 0.0122 moles. Now we're all set to find the molarity. So capital M is equal to 0.0122 moles divided by, and I have practiced using this tablet, trust me, the liters of solution, so 0.10 liters, and we get the molarity of the solution is equal to 0.122 molar, or moles per liter. All right, so temperature effects. Solids and liquids behave differently than gases do. So if the solute is a liquid or a solid, solubility, or the number of grams that you can dissolve per 100 grams of water, increases as temperature increases. And so you can see here we have sodium nitrate. You can see it increases quite a bit. Potassium nitrate, it increases. Even sodium chloride, which is relatively flat, does still increase a little bit. If you notice, NH3, which is normally a gas under most circumstances, decreases, and that's because it is a gas. So as the temperature increases, the solubility of a gas decreases. And over here I have several gases. So I have nitrogen monoxide, and then oxygen gas, carbon monoxide, and you can see they all decrease at about the same rate. The reason why this is true is because the gas molecules are gaining kinetic energy, which allows them to more readily escape from the liquid phase rather than redissolve in it. So then we go on to the last part, where we're going to talk about how pressure affects the solubility of a gas. So Henry's law, it's another gas law, says that the solubility of a gas is directly proportional to the pressure of the gas above the liquid. So if the pressure doubles, the solubility will roughly double. So I have a media clip where it shows a gas in a liquid solvent in a piston chamber, and we allow the piston head to drop, and you can see that the volume of the gas above the liquid solvent is cut in half, which means that the pressure has roughly doubled. So let's make a few assumptions. Just to make the math easier, we're going to assume that our initial pressure of the gas was 1 atmosphere, And then we're also going to assume that the number of particles that are shown in this media clip is going to be proportional to the amount that has dissolved. And so initially we had 6 particles dissolved in the solvent under the 1 atmosphere of pressure. And then afterwards, there's a range of particles that show up in the animation. It ranges between 12 and 16, so we're just going to pick the average value of 14 particles are dissolved in the solvent after we have increased the pressure. So let's use Henry's law to calculate what the final pressure is. So plug in the numbers and solve for the final pressure, and it's 2.3 atmospheres. So that kind of goes to show that this animation was a pretty good demonstration of Henry's law. We cut the volume in half, and the pressure increased, as did the solubility of the gases. So to wrap up everything we've talked about in this lesson, the choice of whether you use mass percent, volume percent, or mass volume percent depends on the phase of the solute in the solvent and the intended use of the solution. Molarity is the most common concentration unit used in chemistry because it has those moles in it, which makes it work with all of the stoichiometry stuff that we've been talking about. And then just to be sure that when you're talking about the volume for volume, mass volume, and molarity, you're talking about the total volume and that you have the correct units. So I hope you learned something new about determining solution concentrations today. Thank you for listening.